3.2, we're going to talk about the mean value theorem. Now, the motivation for this section is that when we try to find critical numbers of a function, those critical numbers can be very difficult to find, and also there's no guarantee that they will even exist. So what these next two theorems do, they try to facilitate the existence of such critical numbers. Okay, and of course, mean value theorem, very important theorem, and it's used in proof of other theorems later on in second semester calculus. Okay, even in our course, we may use it once or twice again before it's all done with it. So we're going to look at a special case of mean value theorem called the Rules Theorem, named after Michael Rolle, the late 17th, early 18th century mathematician. And again, what this theorem does, it provides sufficient condition for the existence of critical numbers. So here it goes. Now, for Rolle's theorem, it does require that the function is continuous and that it is differentiable. Now, continuity is over a closed interval and differentiability over an open interval. Now, if the function turns out to be differentiable on a closed interval, that's fine, but there's no need for endpoint differentiability here. Okay. Now, if f at a equal f at b, that means the 2 points, these 2 points on my chart, on my graph, have the same value, the same ordinate, if you will, on the graph, then Rolle's theorem says that there's at least one point C along the x-axis inside of that open interval from A to B, such that f prime at C is 0. That means the tangent line is horizontal. So I have a drawing here for you, and hopefully this will illustrate what the Rolle's theorem is telling us. Now, it's actually not difficult to prove this theorem. The fact that f at A equals f at B over the closed interval by extreme value theorem, that means there should be at least a number C in there where f prime at C is 0, right? And because the function is either above or below f at A and f at B, in this case I have it below, therefore again, by extreme value theorem, it makes sense that there has to be a point where f prime at C is 0. The proof of this is in the book if you're interested in. I just kind of mentioned it. So that's what Rolle's theorem says. Now, the mean value theorem kind of extends that. Again, Rolle's theorem is a special case of mean value theorem. But for mean value theorem, again, we assume that we have a continuous function on a closed interval and differentiable on the open interval. Then by mean value theorem, there's at least a number C inside of that open interval such that f prime at C equal to f at B minus f at A over B minus A. Okay, now remember, f at B minus f at A, that would give you what the change in the value of the function, and B minus A, you can think of it in the form of some kind of a delta x here, right? So we do have the idea of rise over run, and more closely this would be the slope of a tangent line, right? That's what that is. So let me illustrate this for you now on a graph. The right side of this equation actually gives you the slope of a line through 2 points at A, FA, and B, F at B. So let me actually show you what I mean here. So here, let's say I have a graph like this, and suppose this is A and this is point B. Okay, now I'm going to draw a secant line. Okay, a secant line through these 2 points. Here's f at A and here's f at B. Okay, the note for mean value theorem, f at A need not be equal to f at B. But if it becomes equal, then that's when f prime C becomes 0, and that hence you have a special case which is known as Rolle's theorem. So here I have drawn this line. Now this is a secant line, right? A secant line is a line that connects 2 points on the graph of a function. So the red line here is a secant line. Now, the slope of this secant line, right, the slope of this secant line is indeed f at b minus f at a over b minus a, right? That's what the slope of a secant line. Now, I should be able to, according to mean value theorem, be able to draw at least one line where f prime at c, the slope of a tangent at c, would exactly equal to slope of the line that you're looking at, the secant line. Now for this one, I'm going to use a different color. Let me use, I'm going to use blue. There you go. Or actually, I have blue. Let me use a different color. How about if I use maybe, I don't know, green? Okay, so here's what I'm going to do. I'm going to actually draw these. Now, any tangent line I draw to the curve, it's got to have the same slope as the secant line. So, for example, this would be a line that has the same slope as the red line. It could be here, could be here. See, I have all of these lines that are essentially parallel, right? Parallel to the secant line. But none of those are tangent to the curve, right? Every one of them actually is crossing the curve, right? These lines. So I should be able to find a very special line that is tangent. Tangent, remember f prime, that's the tangent line at some point C here. And I'm going to go, let's say, so I'm drawing a tangent line here. And if I move this tangent line close to the curve, see right now it's crossing it here, so it's not tangent. But if I move it in this direction, if I bring it closer and attach it to my curve now, right, the tangent line, it's going to look like this, right about here. And there, that's pretty much the tangent line at that point. The slope of this line is the same as the slope of the secant line, the red line. Yeah, I'm meaning it to be parallel to the secant line. So there you go, that's the point, and this is where C is. You see that? And that's what the mean value theorem says. Now, is that the only place? No, I can see for this one, if I come now, here's a parallel line to the red line. Let's go in this direction now. Move in that direction. Okay, and as I get closer and closer, there you go, that's pretty close to where it should be, right? The tangent line. So it looks like I'm able to actually find another tangent line for this one right in here. And there you have it. That line is also parallel to the red line, and so is this line. So there's actually two C's in this one. So I'm going to call this C1, and this other point here would be C2. And there you have it. C1 and C2, there are 2 points in this case inside of that open interval where the slope of the secant line and the tangent lines are equal. And that's what the theorem also says, that there's at least one inside of that interval. So let's take a look at some consequences of the mean value theorem for us, and then we'll look at some actually examples from the exercises. So here's an interesting theorem, the consequence of the mean value theorem. We know the derivative of a constant function is 0, right? But the converse of this is also true if you use mean value theorem. Now here's what the converse is, itself another theorem. If the derivative f prime of x equals 0, right, means the slope of a tangent line is 0, the tangent line is horizontal at that point. If f prime of x equals 0 for all x's, this is for all x's inside the open interval, not that some just c, for all x's in the interval, if f prime at any point is 0, then f is a constant function on that open interval. F is constant on a to b. So for example here, what we could do is we can choose, for example, a closed interval x1, x2. This would be like the proof of the theorem. Okay, x1, x2, and we're going to choose x1 to be less than x2, of course, right? And x1, x2, we're going to make him be inside of that open interval. Okay, now this is a closed interval, and because the function is continuous, therefore we can say by mean value theorem f prime at c equals f at x1 minus f at x2 divided by x1 minus x2. You can write it as f at x2 minus f at x1 over x2 minus x1. It doesn't matter. But there you go. Now we are told that f prime of x is 0 for any x inside of the interval, and c here, we presume c is inside the interval, of course. So in this case, it is equal to 0. This is by the hypothesis of this theorem. We were told that if the derivative is 0. Now, we just mentioned up here, right? This is called this proof then. Okay, now right up here, we assume x1 is less than x2, and x1, x2 are non-zero numbers. So you're not dividing by 0, in other words, here. Therefore, for this fraction to be 0, this implies that f at x1 minus f at x2 has to be 0. And from this, we get f at x1 equals f at x2 for any x1 and x2. Well, because this is true for all x1 and x2, this implies that f is constant. So the function must be a constant function. So just interesting theorem we can prove using the mean value theorem. We're going to look at another corollary now to the theorem that we just talked about. Here's the theorem, remember. If the slope of a tangent is 0 everywhere on the graph, therefore the function must be a constant function. So this is interesting. Now for this one, let me just kind of do a sketch of what's going on with this one. So suppose here I have two functions. I'm going to make them a copy of each other. So they're supposed to be identical functions. Okay, this is f and g. So they're identical other than their position. Okay, f sits higher than g, but notice they're curved exactly the same shape. So let's say here the slope of a tangent is 0, so is here for that same, at that same point, exact precise point on the x-axis. And let's say here the slope of a line is positive, and so is here exactly at the same time, at the same point, and exact same slope. So suppose this is true now for f and g over the entire domain of the functions, which is whatever that is, not important here what the domains are. As long as x is an open interval, inside an open interval from a to b, then the consequence of this theorem itself is a theorem, is that f of x should be g of x plus k. That means the two functions differ by a constant. Okay, and in this case, this is where the k is, the difference between the two functions. Okay, at every point. And k is a constant. So for this one, we're going to, let's say if we want to prove this one, so I'm going to call, let's say, h of x to be f of x. We're going to define a difference function, f of x minus g of x. Then we'll take the derivative of both sides. We get f prime x minus g prime x. But then we were told if, that's the hypothesis of this theorem, if f prime x equals g prime x, therefore what that means is that you can replace f prime x by g prime x, and the difference will be 0, of course, right? G prime minus g prime is 0. So we just show that h prime of x is 0. And remember, h prime x is, or h of x, sorry, h of x is the difference function. That's what that is. The difference function has the derivative that is 0. So what does that tell us about the the difference function? Well, if the derivative of any function is 0 over the entire domain, that function must be a constant function, right? So that means the difference function is a constant function. So from this we get h of x is constant function. And this implies, remember h of x was f of x minus g of x, right? When we say that's a constant, call it equal k. That's our constant here. And we can solve for f of x. That would be g of x plus k, which is precisely what we wanted to say. So this says f of x can be written as a constant plus g of x or minus g of x. K is any real number, right? So these two functions are separated by constant. You can get to one from the other by adding or subtracting a constant. And that's what that is. Okay. And I believe with this we're done with all the theorems in this section. So I'm going to grab some exercises and we're going to look at some exercises together. Okay, so let's continue on now with the exercises. In this segment of the exercises, I'm going to do 3 problems here for you. Question reads, verify the function satisfies the hypothesis of Rules theorem and on the given interval, and find all values of c that satisfy the conclusion of the theorem. Okay, so remember the conclusion is that you can find a c such that the slope of a tangent equal to the slope of the secant line, right? And since the secant line in case of Rules theorem was a horizontal line, remember f at a equals f at b, so because of that restriction, therefore we want to show that f prime at c equal 0. The slope of a secant line is 0 in for Rules theorem. For mean value theorem, the slope could be something different. Okay, so first, does it satisfy number 2? Let me write number 2. In number 2 we have question 2. G of x is equal to x cubed negative 9x. And the interval goes from -3 to 3. Okay, so whatever again the graph of the function is, if you want you can graph it, but I'm not going to. Not at this point anyway. So what is the hypothesis? Does it satisfy the hypothesis of Rules theorem? Well, hypothesis of Rules theorem was that the function must be continuous on a closed interval and differentiable on the open interval. Well, g of x is polynomial, right? gx is polynomial function, right? It's a 3rd degree polynomial function, and the continuity of it follows from that, so it's continuous. And for the same reason, g prime x is also polynomial, and it too, it's going to be differentiable. Okay, and actually g of x is polynomial and g of x is differentiable also, not just g prime x, continuous, and let me say differentiable. But g prime x turns out to be polynomial function and differentiable. But remember, for the hypothesis, this is all we need, not this part. Okay. Okay, because differentiability of g prime x means second derivative does exist. Okay, but that's not important for Rules theorem. Anyhow, let's now find c such that f prime at c is equal to 0. So for number 2, therefore, we need to verify also another thing. G at -3 should be equal to g at 3. If it's not, then the theorem won't hold. So g at -3, that's going to be -3 cubed, -9 times -3. -3 cubed is -27, plus 27 is 0. G at 3 is going to be 3 cubed, -9 times 3. That's 27 minus 27, it too being 0. These two numbers must be the same. Okay, and they are. So that means we can proceed now. So what do we need to do? We need to find g prime at c. g prime c. Now we take the derivative of the function. That's going to be 3, and at c replace x with c, so that's 3c squared negative 9c. And we're going to set it equal to 0 to find such c. Now to solve this, we can factor 3c, and that'll make it c minus 3 equals 0, and we have c equals 0 or 3. So we're actually, wait a minute, this is c squared, right? Hold on, the derivative is just 9, not 9c. Okay, that's what was wrong. So from this we get 3c squared is equal to 9, and divide both sides by 3, so you get c squared equals to 3, and that's going to be actually no 0 here, plus minus square root of 3 there. So we were able to find c in this case, right? So that's what we have. Okay, let's take a look at exercise number 6. In exercise number 6, here the function is f of t equals t to 2/3 times 6 minus t to 1/3 from 0 to 6. Okay, and again, here you have a case of a function. The first one is cube root of t squared, which is continuous and differentiable from 0 to 6. And the next one is actually cube root of 6 minus t. So put together, this is cube root of t squared times 6 minus t. Now this function is continuous and it is differentiable 0 to 6. And remember, it has to be differentiable on the open interval, and this function is differentiable on the open interval. So now let's actually verify that f at 0 is equal to f at 6. So f at 0 is 0 to 2/3 times 6 minus 0 to 1/3, which is 0, because 0 to 2/3, 0 times anything is 0. Now f at 6 to 2/3, that's cube root of 36 times 6 minus 6, which is 0. To 1/3 will remain 0 times whatever, that's 0. So we just show that f at 0 equal f at 6 equals 0. So it satisfies the hypothesis of Rules Theorem. Now we need to find the c so that the slope of a tangent is 0. Right, again, the secant line for Rules Theorem is a horizontal line. F prime at c equals 0. So we need to find f prime t. Using the product rule, that would be derivative of first by second 2/3 t2 negative 1/3 times 6 minus t2 1/3 plus first times derivative of second, which is 6 derivative of 6 minus t to 1/3, that's going to be 1/3. 6 minus t to 1/3 minus 1 is negative 2/3. Don't forget chain rule. Remember, you have inside-outside function, so we're going to multiply by negative 1 the derivative of the inside function. Okay, and then let's see, working this one out, we can actually, let's see, we can factor something here. Let's factor t to negative 1/3, and we can factor 1/3 also from the both fractions. So I'm factoring t to negative 1/3. So for the first expression, and actually both of them have 6 minus t also, right? So let's do 6 minus t to negative 2/3. Factor those negative exponents. Now factoring 1/3 from 2/3, so that's going to leave me with 2. T to negative 1/3 factored. Now interesting, I'm factoring this from 6 minus t to 1/3, right? So how is that possible? Or here's how it's possible. 6 minus t to 1/3 because I'm factoring it out, 6 minus t to negative 2/3, also multiplied by 6 minus t to positive 2/3. See, now it's like multiplying by 1. And I'm factoring this out, right? So all that remains is 6 minus t to 2/3 plus 1/3 is just 6 minus t, right? To the first power. So that's just going to be 2 times 6 minus t. Okay, and from the second expression, we factored the binomial out. It's going to be minus because of -1 at the end. And I'm again in a position where I'm factoring t to negative 1/3, factored from t to 2/3. How do we do that? Do t to negative 1/3, t to 1/3. That's just 1, right? Times t to 2/3. And I'm factoring t to negative 1/3 out, leaving me with t. So that's just going to be minus t. Okay, and that is how you factor these. Now let's see, what's next step? Next we can actually write them with positive exponent. Inside a bracket, let's see, that's going to be what? It's going to be 12, right? It's going to be 12 minus t, well, 2t, negative 2t, and t is negative 3t, divided by 3t to 1/3, 6 minus t to 2/3. I'm rewriting them with positive exponents. Now in the numerator I can factor a 3, so that's going to make this 4 minus t, right? All over 3t to 1/3 times 6 minus t to 2/3. The 3's will cross out, and there you go, that is the derivative. Now we need to find c, right, in this case. So this is f prime t. For Rules theorem, we will have to do f prime at c equals 0 and find c. That's what we want to do. So f prime at c, therefore, is going to be 4 minus c divided by c to 1/3, 6 minus c to 2/3. And again, we're going to set it equal to 0. And in a fraction, the only way a fraction can be 0 is if the numerator is 0. Denominator cannot be 0 because of division by 0. So that means 4 minus c has to be 0, or c must be 4. And 4 is in the interval from 0 to 6. Okay, so there you have it. And that's what that is. This was exercise number 6. Now let's take a look at number 8. Okay. And I'm going to move this one down below this part. There, so it's not in the way. We'll use it in just a few moments. In exercise number 8, here we have f of x is equal to cosine 2x minus 1, right? And the interval that we were given is from 0 to pi. That's minus 1 from 0 to 2 pi. Okay, so let's proceed again. F at 0 is cosine of 0 minus 1, which is 1 minus 1, or 0. F at 2 pi is a full circle back to that point, so you're going to get exactly the same result, 0. Okay, now f is continuous, and why? Because cosine is continuous. Minus 1, well, 1 is a continuous function, so that's why it's continuous. And it is also differentiable. So it's continuous from 0 to 2 pi, and it is differentiable from 0 to 2 pi because, again, trig functions are differentiable, right? over the respective domain because they're all continuous over the respective domain. I know there are discontinuities with tangent, cotangent, cosecant, secant, but for sine and cosine, we're talking about cosine here. It is continuous from 0 to 2 pi and differentiable from 0 to 2 pi on the open interval. And you can also argue that f of x cosine 2x minus 1 is just a cosine that is shifted down 1 unit, so it doesn't affect this continuity. Or you can also argue that you have difference of two continuous functions that would be continuous, however we say it. So it meets the hypothesis of Rules Theorem. It satisfies it. And now we need to find f prime at c. F prime at c, that's cosine of, derivative of cosine is going to be negative sine 2c, right, times chain rule derivative of inside. 2c is going to be 2. Derivative of negative 1 is 0. We're going to set it equal to 0 to solve for c. So from this we get sine 2c, or 2 sine 2c equals 0. You can multiply both sides by a negative, the negative drops out. Now 2 times sine 2c is 0. Well, 2 cannot be 0, so that means sine 2c is 0. So we're looking at zeros of sine function are k pi, right? So we're going to set 2c must equal to, or n pi, where n is an integer, right? Now our focus is on 0 to 2 pi here, right? On 0 to 2 pi, so that's what we're going to focus our attention to. Therefore, c would be n pi over 2, and in 0 to 2 pi, so we're going to choose c to be just 90 degrees pi over 2. Right? There are other values, multiples of pi over 2, where we can find c, but the question asks from 0 to 2 pi. And there you have it. Now let's take a look at this next example in this next segment. In exercises 9 through 16, verify the function satisfies the hypothesis, this time of the mean value theorem, on a given interval, and find all values of c that satisfies the conclusion of the theorem. Now remember again, the hypothesis of mean value theorem was that f must be continuous on a closed interval, differentiable on the open interval. That's it. And let's take a look at, for instance, number 10. So in exercise number 10, the function f of x is equal to x cubed negative 2x squared. The interval is from negative 1 to 2. Now f is polynomial again, right? And so I'm just going to say, since f is polynomial, therefore it will be continuous and differentiable. No need for f prime here to be, although f prime is polynomial again, and it too is continuous differentiable, but that's not what the mean value theorem requires. This is what it requires. So it's continuous again on the closed interval, and it's differentiable on the open interval because it's a polynomial function. Okay. Now, for mean value theorem, we said f prime at c is going to equal to f at b minus f at a divided by b minus a. Correct? Now, in number 10, a and b, a is the lower limit, b is the upper limit of that interval. Now, f at b, that means f at 2. F at 2 is 2 cubed minus 2 times 2 squared. That's going to be 0. F at negative 1 is going to be negative 1 cubed minus 2 times negative 1 squared. That's negative 1 minus 2, because negative 1 squared is 1. So negative 1 minus 2 is going to be negative 3. Okay, this is going to give us the slope of a secant line through point negative 1. Let me write this as a point. So my point is -1, -3, and 2, 0. So if we draw a secant line, so 2, 0 is here, -1, -3 is here, so there you go. That's going to be a secant line through whatever that curve looks like, right? -1, -3, and this is 2, 0. That's just a secant line, whatever the graph of this thing looks like. There you go. It may look something like this. But we found we have the points on the secant line. Now, having those points, we can find the slope of a secant line, right? So f at b minus f at a over b minus a is going to be the slope of a line through 2 points, -3 minus 0 over -1 minus, I'm doing b minus a, it doesn't matter, but okay, so that's going to be f at 2, which is 0 minus -3 f at a over b minus a is -1. That's going to be 3 over 3 or 1. That's the slope of a tangent. So now we need to find f prime at c, right? F prime at c equals to that. We haven't found the derivative. F prime at c would be, the derivative of the function is 3c squared -4c. We're going to set it equal to 1, which is the slope of a secant line through those 2 points. And then we can solve this quadratic equation. We have 3c squared -4c minus 1 equals 0. And let me use quadratic formula, -b plus or minus b squared minus 4ac. I'm using the quadratic formula, divided by 2a. Okay, so this is going to be 4 plus or minus, the radicand is going to be 28, right? That's 16 plus 12. 28 divided by 6. Now 28 is 4 times 7, so that's 4 plus minus 2 root 7 divided by 6. Divide the 2's out and we get 2 plus minus rad 7 over 3. Okay, now square root of 7 and 2 plus root 7 divided by 3. Let's see. Now both of these numbers, by the way, if I calculate what 2 plus root 7 over 3 is, so this would be equal to, one number is about 1.55, the other one is -0.22. The 1.55 is 2 plus root 7 over 3, the bottom one is 2 minus root 7 over 3, which is -0.22. Now both of these are in an interval from -1 to 2, right? Because that's the interval in open interval from -1 to 2 in number 10. So there you go. We found two values of c that satisfy the conclusion of the mean value theorem. Okay, so the answer is that. Okay. There, that's the answer to number 10. Let's take a look at another one here. How about let's take a look at, I don't know, number 13 is odd. Let's look at number 14. Okay, in number 14 again, we have the sine function here, like from 0 to pi over 2. Number 14, f of x is sine x, 0 to pi over 2. Okay, now again, f is continuous and differentiable on a closed and continuous on a closed, differentiable on open interval, because it's a trig function, that's why. And then f at 0 is going to be sine of 0, and that's going to be 0. F at pi over 2, sine of 90 degrees is 1, right? Now, let's see. Therefore, we can say that f prime at c is going to equal to f at b b minus f at a over b minus a. That's what we're doing. F prime, derivative of sine is cosine, at c is cosine c, equals f at b. Remember, the lower limit of the interval is a, the upper limit is b. So that's going to be that's going to be the function. That's going to be, again, sine of pi over 2 minus sine of 0, which we did here, right? That's what these are. That's why we calculated those. And we have those numbers. Equals, that's going to be 1 minus 0 divided by pi over 2 minus 0, which is pi over 2. And we have cosine of c equals 1 over pi over 2 is 2 over pi. Okay, cosine is going to be 2 over pi. So that means c is going to be arc cosine or cosine inverse of 2 over pi. Right, that's what c is going to be. Now, it's not a special angle, but using a calculator, I find this c to be approximately equal to about 0.9 radians. Okay, so that's what c is. C is a real number. Radians means real number. And there we were able to find c. Let's try one last one here. Well, from that segment, yeah, number 16, I guess that's all of them. Yeah, that's all we want to do in this section, just the first 16 problems. Let's do g of t sine t over 1 plus cosine t. Okay, so we have g of t sine t over 1 plus cosine t. Okay, and now for this one, this was number 16, right? And we're given, again, 0 to pi over 2. Again, g is continuous and differentiable over the closed interval for continuity, open interval for differentiability. And this because it's a ratio of two continuous functions in this case. Okay, and in that 0 to pi over 2, the function is continuous in number 16. Now we need to find g prime at c. Okay, g prime at c, the derivative is going to be square the denominator, cosine c squared, repeat the denominator, times derivative of the numerator, derivative of sine is cosine, minus the numerator times derivative of 1 plus cosine is 0 minus sine. And all of this is happening at c. Okay, so now I can simplify this thing. Let's see. In the numerator, I have sine squared c, right? Sine squared c. And hold on, let me simplify this. Okay, actually now I see it's pretty easy actually to do this one, simplify it. So I have 1 plus cosine c squared. In the numerator, if I distribute cosine from the right here, distribute, I get cosine c plus cosine squared c. The double negative on sine makes positive, right? And then I have sine squared c. Now using the Pythagorean identity, we get 1 plus cosine c over 1 plus cosine c squared. So it's going to work out nice in the end. Therefore, g prime at c is simply 1 over 1 plus cosine c. And we're going to set it equal to like f at b minus f at a over b minus a. Remember, for mean value theorem, that's the slope of the secant line. F at b and a, we haven't done those, so In this case, our f is g, so let me correct that. That's going to be g, because the function is g, not f. Okay, so g at b, that would be sine, let's do this, g at pi over 2. Well, that's going to be sine of 90 degrees over 1 plus cosine of 90. So that's going to be 1 over 1 plus 0, or 1. So that's going to be 1 minus g at a, that's g at 0, which is going to be sine 0, 1 plus cosine 0. That's 0 over 1 plus 1, or 0. And b minus a is again pi over 2 minus 0, so that's 2 over pi again. And this time though, the equation is 1 over 1 plus cosine c equals 2 over pi, right? And we can solve this one now, right? So how are we going to solve this one? Let's cross them, or actually I'm going to flip it, it will be easier. 1 plus cosine c is going to be pi over 2, right? Flip both fractions, because we need to isolate c, right? So cosine of c is pi over 2 minus 1. There you go. Therefore, c is going to be arc cosine or inverse cosine of pi over 2 minus 1. Okay, so this will be the exact value. And if you use like a calculator, let me try it on my calculator here. So make sure we are in radian mode, okay? I'm in radian mode doing this. And inverse cosine, parentheses, pi over 2 minus 1, close print, enter. Okay, I got about 0.96 rounded. Okay, and there you have it. So we're able to find again c according to mean value theorem. Okay, and there you go. So we are done with this section 3.2.